determine the general lighting load for a 1800 square foot house, we begin by applying a standard estimation of 1 watt per square foot. This estimation comes from the National Electrical Code, or NEC, which provides guidelines for safe and efficient electrical installations. Thus, the calculation for the general lighting load is 1800 square feet multiplied by 1 watt per square foot, resulting in 1800 watts. This figure represents the total power expected to be consumed by general lighting throughout the house, including living rooms, bedrooms, hallways, and other common areas. Next, to determine the minimum number of 120-volt 2-wire branch circuits required for this general lighting load, we need to consider the amperage capacity of standard branch circuits. The typical 15-amp branch circuit at 120 volts can handle a maximum load of 15 amps multiplied by 120 volts, which equals 1800 watts. Similarly, a 20-amp branch circuit at 120 volts can handle a maximum load of 20 amps multiplied by 120 volts, which equals 2400 watts. Given the general lighting load of 1800 watts, we can calculate the required number of branch circuits as follows. For 15-amp circuits, we divide the total lighting load of 1800 watts by the capacity of each circuit, which is 1800 watts. This yields 1, indicating that one 15-amp branch circuit would technically suffice. However, it is generally recommended to have at least 2 15-amp branch circuits to avoid overloading a single circuit and to provide some redundancy. Alternatively, for 20-amp circuits, we divide the total lighting load of 1800 watts by the capacity of each circuit, which is 2400 watts. This gives us 0.75, meaning that a single 20-amp branch circuit is sufficient to handle the general lighting load. Again, consider that it is generally recommended to have more than one circuit. Now, let's move on to calculating the net load for the house. The net load is the total electrical load of the house after applying any applicable demand factors or adjustments. In this case, we have a general lighting load of 1800 watts, an 11 kilowatt range which is 11,000 watts, and a 6 kilowatt 240 volt dryer which is 6,000 watts. The total connected load is the sum of these individual loads, which is 1800 watts plus 11,000 watts plus 6,000 watts, equaling 18,800 watts. According to standard practices outlined in the NEC, the first 3,000 watts of the total load are taken at 100%, while the remaining load is subject to a demand factor. To calculate the net load, we subtract the first 3,000 watts, which are accounted for at 100% from the total connected load. This leaves us with 18,800 watts minus 3,000 watts, which is 15,800 watts. In many cases, a demand factor is applied to this remaining load depending on the specific application and the requirements of the local electrical code. For example, if a demand factor of 35% is applied to the remaining load, the net load would be calculated as follows. First, we take 3,000 watts at 100%, which is 3,000 watts. Then we take the remaining 15,800 watts at 35%, which is 15,800 watts multiplied by 0.35 equaling 5,530 watts. The net load is then the sum of these two values, which is 3,000 watts plus 5,530 watts, equaling 8,530 watts. However, in this specific scenario, we are told to subtract the first 3,000 watts from the total connected load, so the net load would be 22,400 watts minus 3,000 watts, equaling 19,400 watts. Let's recap the steps involved in these calculations. Firstly, we determine the general lighting load by multiplying the square footage of the house by the appropriate watts per square foot, in this case, 1 watt per square foot. Secondly, we determine the minimum number of branch circuits required to serve the general lighting load, considering the amperage capacity of each circuit. Thirdly, we calculate the total connected load by summing the individual loads of all major appliances and lighting. Finally, we calculate the net load by applying any applicable demand factors or adjustments as specified by the electrical code. Now let's delve deeper into the concept of demand factors and their application in electrical load calculations. Demand factors are used to account for the fact that not all electrical loads in a building operate at their maximum capacity simultaneously. For example, it is unlikely that all lights, appliances, and equipment in a house will be running at full power at the same time. The NEC provides tables and guidelines for applying demand factors to various types of loads based on their usage patterns and characteristics. These demand factors are typically expressed as a percentage, which is multiplied by the connected load to determine the demand load. The demand load is the maximum amount of power that is expected to be drawn at any given time, and it is used to size the electrical service and distribution equipment for the building. In the case of residential dwellings, demand factors are commonly applied to general lighting loads, appliance loads, and heating and cooling loads. The specific demand factors used will vary depending on the size and type of dwelling, as well as the local electrical code requirements. Let's consider an example of how demand factors might be applied to the electrical load calculation for our 1800 square foot house. Suppose that the local electrical code allows for a demand factor of 40% to be applied to the general lighting load. In this case, the demand load for general lighting would be 1800 watts multiplied by 0.40, which equals 720 watts. This means that the electrical service only needs to be sized to handle 720 watts of general lighting load rather than the full 1800 watts. Similarly, demand factors could be applied to the appliance loads, such as the range and dryer, to further reduce the overall demand load. The specific demand factors used for these appliances would depend on their size and usage patterns, as well as the requirements of the local electrical code. It is important to note that the application of demand factors requires careful consideration and a thorough understanding of the electrical code. Incorrectly applying demand factors can lead to undersized electrical services, which can result in overloaded circuits, voltage drops, and other electrical problems. Therefore, it is always recommended to consult with a qualified electrician or electrical engineer when performing electrical load calculations and designing electrical systems. In addition to demand factors, there are other factors that can affect the electrical load calculation for a building. These include the type of occupancy, the number of occupants, the climate, and the presence of any special equipment or loads. For example, a commercial building with a high concentration of computers and electronic equipment will typically have a higher electrical load than a residential dwelling of the same size. Similarly, a building located in a hot climate will typically have a higher electrical load due to the increased use of air conditioning. When performing electrical load calculations, it is important to consider all of these factors to ensure that the electrical system is properly sized and designed to meet the needs of the building. This will help to ensure the safety and reliability of the electrical system, as well as the comfort and convenience of the occupants. Let's now discuss the importance of proper branch circuit design and wiring. Branch circuits are the individual circuits that supply power to the various outlets, lights, and appliances throughout a building. These circuits are typically protected by circuit breakers or fuses, which are designed to interrupt the flow of electricity in the event of an overload or short circuit. Proper branch circuit design and wiring are essential for ensuring the safety and reliability of the electrical system. Incorrectly sized or wired branch circuits can lead to overloaded circuits, voltage drops, and other electrical problems. Overloaded circuits can cause the circuit breaker to trip frequently, which can be a nuisance and can also damage the electrical equipment. Voltage drops can cause lights to dim, appliances to malfunction, and motors to overheat. To ensure proper branch circuit design and wiring, it is important to follow the guidelines and requirements of the NEC in the local electrical code. These codes specify the minimum size of conductors, the maximum number of outlets or lights that can be connected to a single circuit, and the proper methods for wiring and grounding the circuits. It is also important to use high-quality electrical components and materials, and to ensure that all connections are properly made and tightened. In addition to following the code requirements, it is also important to consider the specific needs of the building and its occupants. For example, a kitchen will typically require more branch circuits than a bedroom due to the increased use of appliances and equipment. Similarly, a home office will typically require more branch circuits than a living room due to the increased use of computers and electronic devices. By carefully considering the specific needs of the building and its occupants, it is possible to design branch circuits that are both safe and convenient. This will help to ensure that the electrical system meets the needs of the building and its occupants for many years to come. Let's also discuss the importance of proper grounding and bonding. Grounding and bonding are essential for ensuring the safety of the electrical system and preventing electrical shocks. Grounding provides a path for fault current to flow back to the source, which causes the circuit breaker to trip and energizes the circuit. Bonding connects all of the metal parts of the electrical system together, which ensures that they are at the same potential and prevents voltage differences from occurring. Improper grounding and bonding can create a dangerous situation where a person can receive an electrical shock if they come into contact with a metal part of the electrical system. To ensure proper grounding and bonding, it is important to follow the guidelines and requirements of the NEC and the local electrical code. These codes specify the proper methods for grounding and bonding the electrical system, as well as the minimum size of grounding conductors and bonding jumpers. It is also important to use high-quality grounding and bonding components and to ensure that all connections are properly made and tightened. In addition to following the code requirements, it is also important to consider the specific needs of the building and its occupants. For example, a building with a swimming pool or a spa will typically require additional grounding and bonding measures to protect people from electrical shocks. Similarly, a building with sensitive electronic equipment will typically require additional grounding and bonding measures to prevent damage to the equipment. By carefully considering the specific needs of the building and its occupants, it is possible to design a grounding and bonding system that is both safe and effective. This will help to ensure the safety of the building and its occupants for many years to come. Finally, let's discuss the importance of regular electrical inspections and maintenance. Regular electrical inspections and maintenance are essential for ensuring the safety and reliability of the electrical system. Electrical systems can deteriorate over time due to wear and tear, corrosion, and other factors. Regular inspections can help to identify potential problems before they become serious, and maintenance can help to prevent problems from occurring in the first place. During an electrical inspection, a qualified electrician will typically check the condition of the wiring, the circuit breakers, the outlets, the lights, and other electrical components. They will also test the grounding and bonding system to ensure that it is functioning properly. If any problems are found, the electrician will recommend repairs or replacements as needed. Regular electrical maintenance can include tasks such as tightening connections, cleaning components, and replacing worn or damaged parts. By performing regular electrical inspections and maintenance, it is possible to keep the electrical system in good working order and to prevent electrical problems from occurring. This will help to ensure the safety and reliability of the electrical system, as well as the comfort and convenience of the occupants. In conclusion, calculating electrical loads for a 1800 square foot home involves several steps, including determining the general lighting load, the minimum number of branch circuits required, and the net load. It is important to follow the guidelines and requirements of the NEC and the local electrical code, and to consult with a qualified electrician or electrical engineer when performing electrical load calculations and designing electrical systems. By taking these steps, it is possible to ensure that the electrical system is properly sized and designed to meet the needs of the building and its occupants, and that it is safe and reliable for many years to come.